Hi everyone. In this video we are going to learn about this concept called the derivatives of functions. This relates to sections 2.7 and 2.8, and in section 2.7 we are going to compute this thing called the derivative at some fixed value of x. So you're going to treat this value of x to be some fixed value, a constant, say a. But as opposed to that, in section 2.8, we start to allow that x value to vary. Now, as far as this concept goes, this relates very closely to what we were talking about at the beginning of this quarter. I am referring to this whole idea of trying to find the equation of the tangent line to the graph of some function. So I want us to go back and look at the picture one more time. So here, let's just suppose that you have this function given to us. Here you see that the f of x equals -1/2 x minus 3 quantity squared plus 5. So this is definitely a quadratic. And because of that negative leading coefficient, this parabola is opening down and so forth. Now you do see already some fixed point. I'm labeling that as point A, and you see the tangent line drawn there to that graph, which is the red line. So it looks like in this particular case, the fixed value that I'm interested in this 1.5, and if you were to plug in that x equals 1.5 to that function, you're going to you can verify that it's going to be 3.875, and that's not rounded in any way. That is the exact value. So how did we actually try to come up with the equation of this line? And in order for us to do that, you remember that we needed to try to find the slope of this tangent line. And that was the challenge, wasn't it? Because only thing that we know is this fixed point A. And if I only have that one point, then there's no way that we can find the slope of this line that we need to find the equation for. So what we did back then is to take just another point on the graph. So I am gonna just pick a point. So here's another point. Now, as long as that point is on the graph, and if I'm just picking some value of x to plot another point, I can definitely find the coordinates of that point. And once I have those two, then I can definitely find the slope of the line that would go through these 2 points. And from that, I could come up with the equation of the line, and that line is given by that blue line right there. And remember that this blue line is called the secant line as opposed to the tangent line, because it is actually intersecting the graph at 2 different points. Now what I do know is that if I were to look at the distance between the first x value and the new point that I took, it's, in this case, looks like it's h units apart. And then what we can do though is that since that line isn't exactly what we want, we are going to allow that the value of h, distance h, to shrink down to 0, right? So we're basically essentially allowing that point to get closer and closer and closer to that point A without actually getting to A. But if I can actually allow it to get to A, that's where that blue line turns into the tangent. But in order for us to calculate the slope, you don't want those 2 points to coincide. So that's really where the notion of the limit came from. Now I would like you to kind of have this image in your mind, and we are now about to define exactly what the derivative of a function is at some given point A. Okay, so in order for us to try to come up with the slope of that tangent line, as we did earlier, we can take another point right here, let's say. So this is the unknown coordinate x, And so assume that this distance between a and x is given by some value h. So another way of expressing that coordinate x is going to be a plus h, because you need to move h units starting from a. Now with that, I believe that we can try to find the slope of the secant line given by this blue line. So sorry about that, the fact that it doesn't look as straight, but let's say that this is the secant line. Okay, so let's just talk about the slope of the secant line. One way to do that is for us to, so let's say this is m of the blue line. It is definitely changing y over changing x. So changing y value, it is going to be, now one way to do that is to evaluate f at exactly x minus f of a. A is the fixed value, so f of x minus f of a, that gives me the change in y value. Divide that by changing x, which is x minus a. But now that fraction is only going to give us the slope of the secant line. So in order for us to turn this into the slope of the tangent line, so let's denote that as m sub TL to denote that this is the slope of the tangent line. What we need to be able to do then is to take the limit of this fraction, and what we need to be able to do is to let that value of x to get closer and closer and closer to a. So another way of writing that is to take the limit as x goes to the value a of exactly that same expression, changing y, which is f of x minus f of a, over changing x, which is x minus a. Now I am going to write the same expression in a different way, and let's just use this the expression a plus h to denote that the value of x that's h units away from a. So now in that case, I can write the same exact thing as the limit as this distance h goes to 0. That's when x approaches a. So write limit as h goes to 0 of, again, changing y over changing x. So instead of writing f of x, I can write f of a plus h minus the original y value, which is f of a, all over. Now instead of writing x minus a, I can just simply write h. So this limit expression, limit as h goes to 0 of f of a plus h minus f of a all over h. Now again, I want to remind you that in this expression, a is some fixed value, so a is supposed to be a constant. This is exactly the definition of the derivative of f of x at x equals a. Now, as you know from the previous sections, that when you're trying to evaluate the limit may or may not exist. So this definition is actually not quite complete unless I add this statement, if this limit exists. And the notation for the derivative is going to be f prime of a. So if you're trying to denote the derivative of the function f of x at some particular value x equals a, you want to use this f prime of a. So you use the apostrophe there. So that's the notation for that. So now let's do a simple example. Suppose that you are given this function f of x equals, say, x squared. And if I want to find, say, f prime of, say, 2. Now again, this is by definition. This is going to be the limit of the changing y over changing x. So, using the definition, this is the limit as h goes to 0 of f of, now a in this case is 2, so it's going to be 2 plus h minus f of 2 all over h. Now I can definitely rewrite both of these terms in the numerator. If I plug in 2 plus h into x, I get, let me just write this limit notation there. So if I put 2 plus h into that x, I get 2 plus h quantity squared minus f of 2, just plug in 2 into x, so I get 2 squared all over h. Now that is going to be limit as h goes to 0 of, now expanding that 2 plus h quantity squared, you should get 4 plus 2 times 2 plus h, so that's going to be 4h plus h squared. Now if you want to just do 2 plus h times 2 plus h to see what that quantity is, but maybe some of you remember how to square a binomial, and minus 2 squared is going to be 4, so all over h. Now you can definitely see that the 4 minus 4 will cancel each other out, and you get limit as h goes to 0 of 4h plus h squared all over h. Now if you check the form of this, you realize that this is 0 over 0 form. Now this will turn out to be the case for all the derivative computation. Derivative is because you're trying to get that one point to get closer to another point, it is always going to end up with 0 over 0, but you know how to handle this. In this case, I guess what you can do is to factor out the h from the numerator, so I get 4 plus h, and the denominator is h also. Canceling that out, you're going to end up with limit as h goes to 0 of this expression 4 plus h. Now this is something that I can plug the value of h in for, so this is going to go to 0, and you end up with this quantity 4. So now that value right there is the derivative of this function f of x equals x squared at x equals 2. Now notice that in this definition, every time we pick this value of a that we have, a is this constant, right? The fixed value of x. I would have to actually replace that a with that particular constant that I choose. But if you look at this computation that we just did, what you need to compute is going to be very, very similar. In fact, identical. The only difference is that constant a. So that's where the definition of the derivative as a function comes in section 2.8. So let me just give you that definition here as well. So in this earlier definition, if we allow that the value of a to vary, so meaning that the one actually fixing that particular point, then we're going to leave that as the variable. So that's why you have this variable x left in this expression. So f prime of x, that's the notation for the derivative of f as a function, and the definition is essentially the same thing as the earlier definition. However, you do have the value a to be replaced by the variable x.